Right, thank you. So yeah, I'm talking about specifically Naproche-ZF, which is my kind of weird new implementation, kind of an experimental theorem prover that I'm working on for my PhD. And I want to jump straight in with examples. So let's see. So this is a so this is a simple formalization in my system. So this is Cantor's theorem, which you've seen probably 1,000 times. But the kind of the two main things that I want you to notice here, as with the Naproche system that Peter showed to you already, we have a proof in natural language, and we have kind of a similar proof granularity as you would find it in kind of informal mathematical proofs. So the idea is that a formalization in Naproche-ZF would still function as a mathematical text. So I kind of want to show you how this works. So basically we go through the proof, and whenever we leave a kind of gap in the proof, something that you as a human reader also need to fill in, then we hand it over to the ATP. So in this case, I'm showing you the gap corresponding to this B is an element of the power set of A. So as a human reader, we kind of have to figure out, okay, so in this case it's fairly easy, right? We know what it means to be an element of the power set, and we know what it means to be a subset of something, right? And then kind of by construction, we're constructing B as a set comprehension using separation. So it's kind of fairly obvious that this is indeed an element of the power set. But you do have to know all these things, right? And in this case, we get a kind of proof task corresponding to this. And sort of at the top of this proof task, we have basically anything that came before. So all previous global theorems, definitions, anything that came before in the text is in principle available. And then at the bottom here, we have local premises. So these are things that either come from the statement of the theorem. So if we start the theorem saying, let n be an even number, then this would be a local premise there. And the other local premises come from previous proof steps. So, for example, by saying, well, suppose not, right, we assume the contrary, and then this becomes an assumption and a local premise. And yeah, and this is kind of handed over to a first-order automated theorem prover, an ATP, like Vampire, for example. And in this case, the problems are very easy for an ATP. This takes a fraction of a second. Hopefully, you also only need a fraction of a second as a human reader for this type of proof step. But of course, you can imagine this in more general cases, it's more difficult. And then finally, the thing I want to point out here is that so in the text, I'm defining B using set comprehension. So this is not first order. We have a set comprehension, and sort of within that term, we have a formula. But of course, I can take an extensional view of B and translate this into this formula, and then again, I'm back in first order, and I can hand it over to the ATP that only understands first order. Right, so I've shown you the kind of the pretty printing, the typesetting view of the formalization. So here's a first peek behind the curtain. So at the top we have the kind of the formalization after typesetting. So this is some stuff about ordinals. And then at the bottom you see the LaTeX that I'm actually writing. And this is what the system actually checks. So I just input the LaTeX into the system, and it checks this, and yeah, it's happy. And maybe another thing to notice here, that sort of towards the end of the proof, so omega is transitive, thus omega is an ordinal, hence omega is an omega, contradiction, all these things are kind of ATP tasks in the same way that the E is an element of the power set of A that was an ATP task. And yeah, we kind of collect all these, hand them over, the ATP says yes to all of them, and then we're happy and move on. Right, so I'm kind of in the luxurious position of not having to explain too much about controlled language, because Anna and Peter already showed it a couple of days ago, but I kind of want to give my favorite example to show this kind of phase transition from unrestricted language to controlled language. So this is a random exercise from Naproche's set theory, and we have this conditional statement. And so the first problematic thing here from the controlled language point of view is a quantification that's maybe not so clear, right? So we're quantifying over something, but we're not really saying what it is. And in this case, it's fairly easy to figure out, even maybe syntactically, that the only thing we can quantify over is the alpha. But of course, you can imagine situations where such a quantification relies on more like semantic information or some kind of conventions that you're used to figure out what is the thing that is being quantified over. And the other problem is, of course, the anaphora, the same in the consequent here. And in the consequent, we also have the same kind of vague quantification. So if we kind of go in manually as a human writer and clarify this in this way, then we end up in kind of the fragment of the mathematical English that is in the controlled fragment. And then the system is able to parse it and translate it into a formula, like the one at the bottom. Right, and then here's some more examples. So this is kind of a new feature in my system. There's a way of directly specifying mathematical structures. So I can just say things like, so the one-sorted structure is kind of a built-in thing. It's just a thing that has a carrier and nothing else, so no additional structure, no axioms, nothing. So I can kind of extend this by adding this frame of opens OOV, and then I just say some things about this OOV, right? The usual axioms of the topological space. And then again, the LaTeX markup for this is fairly straightforward. Kind of the weird thing I'm doing here is the structure operations. I'm using kind of LaTeX macros that take an optional argument so that you can omit them in certain situations. So if I say something like, in a theorem, I say, let G be a group, then I don't have to add the G label to all group operations. I can just write the multiplication as is. So this is kind of like some slight LaTeX trickery. But yeah, otherwise, it's mostly standard LaTeX again. And then this is kind of a fun example. So this was, I met a student who did some like first lean experiments, and he did some stuff about inverse semigroups. And he wasn't so happy with this formalization, and he kind of challenged me to formalize it in my system. So it was just like a tiny theorem in inverse semigroups. But to do that, of course, you need to define what it is in inverse semigroups. So we just extend a magma, which is a thing with a binary operation with a bunch of axioms. Doesn't matter too much the details here. But then, so the thing I wanted to formalize was this like simple statement about inverse semigroups. So we have two idempotent elements, and in the setup we need to show that they're equal, right? And this was some kind of medium length lean proof, just like basically getting a bunch of equalities set up. But in this case, in my system, I can just write this theorem, and with a bit of patience, I think this was slightly less than a minute, Vampire is able to prove this. So if I want to be super lazy, I can just hand this off to the ATP and say, well, I'll lean back and relax, and the ATP can prove this for me. But of course, maybe you also want a proof for the human reader. Yeah?
Can you, like, would that just be like exercise for the reader?
Yeah. So there's kind of the implicit thing that if I don't write a proof, then it's left to the ATP. I'll get to the kind of the semantics of the proof in a bit. But yeah, basically, if I just say something like, this is easy, or if I don't write anything at all, it's left implicitly to the ATP. But of course, yeah, like if you see something like this as a human reader, maybe in a more complicated example, you're a bit annoyed if the author doesn't give you a proof, right? So to be nice to the human reader and to maybe like check it more quickly, we start giving a proof. So this is not a particularly beautiful proof. It's kind of a very, it's like very, how should I put this? Kind of slightly stilted language, right? We just choose two witnesses for this thing, and then we just do a calculation, and that's it, right? But it's serviceable enough, and hopefully it's still readable to the human reader, and you can kind of see what's going on. And yeah, and then in this case, because the proof steps that we require of the ATP are much smaller, this again takes like a fraction of a second to check the whole thing, because all the subtasks are very easy now for the ATP, especially since we're like giving explicit hints by referencing previous things. And now we have something that also works for the human. And again, this is the last peek behind the curtain. So this is what I'm writing here. And for the kind of equation typesetting, I'm just reusing standard LaTeX environments like align. And for the referencing, I'm using, again, like standard LaTeX packages like cleverref and hyperref and these things to kind of reference previous things in the document. And yeah, this is how you would write the thing you saw on the previous slide. So let me briefly talk about the natural language understanding part. Again, I'm in the luxurious position of you having seen Anna's talk about GF. So this is basically a grammar fragment from my implementation. So actually, I'm using a library where I can directly specify a context-free grammar in the implementation. So this is a very convenient way for me to implement this. And I kind of split this into two parts. So at the top, we have the dynamic aspect of mathematical language, because at any point I can coin new terminology, I can coin new notation, right? There's no restrictions, right? You can say, something is a foo, something is a blah. There's nothing stopping you, right? So we kind of need to account for that. And then at the bottom, there's sort of the static frame around it, the ways of constructing sentences in this controlled language. And this is not dynamic. This is like kind of manually written as a grammar and frozen forevermore until you edit it again manually. So kind of the example I'd actually give for what might not work with this kind of static fragment is we did a formalization of the appendix of Kelly's topology book, where he does some class theory. And Kelly has the quirk that he says when and only when instead of if and only if. Right? So and if this is not in this kind of static part of the grammar, then the parser would reject such a sentence. Of course, then you're kind of faced with the options. So either I add this silly option of speaking to the grammar, or I just rephrase it, right? And then you kind of have to make a call, like, do you want to clutter the grammar by adding this rule? Is there some kind of ambiguity that you could be adding by extending the grammar? And in this case, of course, there's no big risk, but you can imagine in more complicated cases, kind of extending the grammar definitely will maybe lead to some trouble. And so for the dynamic part, what I'm doing is I kind of, before I parse the text, I scan through it and collect all the vocabulary that is defined. So we basically just look for definitions, and then by the way that something is defined, you can kind of figure out what is the lexical category of this thing. So for example, a noun is kind of always defined like something is a, and then the noun, if and only if, right? And then we can kind of extract this pattern and add it to the grammar. So the grammar is kind of parameterized over these lexical items. And yeah, as you saw in GF with these kind of smart paradigms for guessing plurals from just a singular form, I'm doing something similar, for example, to guess that the plural of this function from x to y is functions from x to y, right? And then, so this is this kind of bracket slash thing kind of indicating the singular plural forms. And so the zero slot is a slot in a noun that is used when we quantify over this noun. So if we say something like all functions f something holds, right, then we kind of have to insert this f into the noun pattern. So this is kind of a placeholder for that. And the 1 and the 2 are the actual argument slots. And kind of like as a dependent noun, like depending on these two parameters. Right, and then we can do the same for all these other lexical categories like adjectives, verbs, but also symbolic material like relation symbols and other types of notation. And then to give you an idea of how the translation to first order logic works, some of this is like fairly straightforward, just kind of simplifying the language. So for example, if we have some kind of relation chaining, like A is less than B is less than C, that gets translated to A is less than B and B is less than C, right? And then there's some kind of conventions, like if we use a set in this kind of weird relation infix notation using like the kind of math rel in LaTeX to get the correct spacing, then you can kind of see, okay, this using like the usual tuple representation of relations in set theory, this means that the tuple xy is an element of R. And then there's like ways of kind of translating more complicated quantifications to simpler quantifications. And so this step with there exists to consider. The meaning of this is that if I say consider, I'm kind of explicitly choosing a witness for an existential statement for the future of the proof. Whereas if I just say, well, there exists, so the sort of literal reading of that means, well, it exists and then I forget about it, right? Because this is kind of a bound variable in the sentence and then in the next sentence it's gone. But of course there's kind of like in some sense maybe like a pragmatic effect, where if I'm telling you there exists something, I'm doing it for a reason, right? I'm not telling you to so that you forget it in the next sentence. So the implicit meaning is, well, yeah, I'm showing it exists, and I choose it as a witness afterwards as well. So this is kind of like a slight pragmatic effect in the system. And of course, there's a way of like anonymous quantifications. Like every set is an under of some Grothendieck universe. I can expand this by adding some variables and making this more similar to a regular formula. And then after we do all these kinds of transformations, we end up in a form that is very close to some logical formula, and then it's easy to translate to a format that these ATPs can understand. So there's some slight language improvements compared to the previous system. The major pain point was like certain ambiguities, like there was no distinction between A, or no lexical distinction between A as a variable and A as the article. So this can lead to some annoying ambiguities. But of course, if we require LaTeX markup, then we can just distinguish them between math and text mode, right? So this ambiguity disappears, and yeah, there's also kind of this requiring math mode in the LaTeX, or using the math mode that we add to the LaTeX to make things show up properly. This also kind of improves error locality. So if we mess up somewhere within a formula, we know, okay, so here the formula ends, and this was sort of the intended end of the formula, and doesn't run on until the end of the sentence or something. And another thing that's a slight improvement is we actually model now a grammatical number correctly. So again, this is like maybe a slightly contrived example, but this removes certain ambiguities. Right? So if we identify singular and plural, if we treat them synonymously, then this kind of the maximum of x and y could be ambiguous, right? If we have both the maximum of x, like treating x as a set maybe, or like a binary maximum operation. If we have both of these things defined somewhere, then so this is potentially ambiguous. But of course, in the second one, we would use the plural form, and then we can disambiguate it like this. Yeah.
What happens if you have ambiguity, or like?
Okay. So yeah, the grammar formalism basically just returns all the possible parses. So if I add an ambiguity to the grammar, I mean, this is kind of what can happen with this dynamic aspect, right? Like there's nothing stopping me of creating notation that is actually ambiguous, right? In that case, the parser would just return all the possible parses, and you would see, okay, so this is ambiguous. And then you can either add like parentheses, things like that to disambiguate things, or like rephrase things, or you actually need to go back and like reconsider the way you're defining your notation or your vocabulary. Yeah.
On the previous slides with the commata and so on,
yeah.
We're seeing out there, if you look at LaTeX that people produce, we have all these full sentence stops and so on in display equations and commata and so on.
Yeah.
You would rephrase that, is that correct?
There's some slight accounting for that to be like to make it slightly more robust, but yeah, there's a kind of a specific way of writing things. So this is like kind of an added complexity to the controlled natural language thing, where there's some kind of expectation of how you write your LaTeX, but we try to like get it as close as possible to what you would write anyway. So if you're like some kind of disciplined LaTeX user.
Those are very few from looking at the archive.
Yes. Yeah, there's certainly an art to writing like a controlled language formalization. Right. Yeah. So this next thing is so we're using, as you saw in the kind of peek back the curtain I showed earlier, we're just using standard LaTeX environments like definition, theorem, and proof. And the way the system works is just it reads through the text and ignores everything outside of these formal environments. So kind of by doing that, we can mix informal content and formal content as we please, right? As long as we kind of keep the formal environments formal, we can, in between them, we can write anything. So this gives us kind of literate formalizations. And of course, you can also do something similar in other proof systems, like Isabel has these proof documents, and there's literate acta and all sorts of things. But here we have the added benefit of the formal already being readable, right? So you don't have this thing where you kind of, I state something in acta, but before that, so for the human reader, you have to explain it first in natural language, right? We don't get this kind of duplication of the form here.
To be fair, they do that in actual math text too, right?
Yes,
oh, you write
sometimes.
some complicated formula and then you restate what you just said in naturally.
Yeah, but this is like slightly less necessary than with other proof systems. Yeah. And then you get the usual, like if you have to do that, then you get the usual problems of like syncing documentation to your implementation, right? Like things might get out of sync, and yeah, and you also have just more stuff in Flutter. And right, so this is like very briefly justifying why we even do this controlled language thing and not just use like machine learning and things like that. So the pragmatic reason is it works well enough for us, right? This is like, it works in Sand, it works in Naproche. Then the other thing is, as you saw with this dynamic thing, right, we can model this quite nicely with these patterns. And this is a lot of sort of what we require to express things in mathematics in a way that is nice. And this is actually easy to model in this kind of formalism. And yeah, as I kind of indicated already when answering Michael's question, like the sort of the pain of writing in controlled language is felt more when writing than when reading, right? As a reader, ideally, the end result is just more or less a mathematical text, maybe in slightly stilted language, but I mean, we've all read plenty of math documents that are in stilted language, so this is not too painful. And of course, if we have a formal grammar, we have a regular parse tree, and we can just translate things in a very straightforward way to first-order logic. And of course, with the proper parser, we also get the benefits of like giving proper parse errors, right? If you make a specific mistake, I can point it out just as with a parser for a programming language and things like that. Okay, so now a bit onto the proving stuff. So maybe like with these proof gaps, you can kind of get to the question of what would be an acceptable proof gap. Right, I think we can all agree that this Fermat's proof gap was not acceptable, right? I think history has shown. But of course, depending on the kind of mathematical maturity of the reader, there are certain proof gaps that are acceptable. So, I mean, I really like these last two, like saying, oh, it's easy, or just check this thing, or just think, right? So these are all from the same paper. I won't name any names. But yeah, this is, I mean, depending on your reader, this might be okay, right? But when we actually want to formalize things, it of course depends on what the computer is able to do. Like, then we get to this kind of problem of what can the computer do, what can the human do? And of course, certain ways of proving things are hard for the computer to follow. Like, and so if we have like some kind of geometric picture and we're waving our hands and we all understand how this, yeah?
Your example of follows by an easy diagram chase, I would say is sort of a tactic proof, right?
Yes, yes.
Do you have any mechanisms for modeling essentially procedural proof strategies?
Not really at the moment. So there's some like very slight things. So for example, there's, I mean, I can maybe jump ahead. For example, there's like some simple tactics like, okay, just apply set extensionality. And of course you could imagine like doing something similar for like category theory where certain like proof methods are built in. But yeah, this is, like the most of the heavy lifting is done by the ATP, which is just like a generic first order theorem prover. Right, so yeah, we have certain types of proofs that are hard for the computer, but of course the computer is also good at things that humans are bad at, right? Like if we have like a reduction to 10,000 cases and they're all easy, then for the computer that's not a problem. Whereas if I give you like a stack of paper and say, here's 10,000 inequalities, check them please, you're going to be pretty annoyed with me, right? So there's certainly a benefit of using a computer in certain situations, and as long as the computer is kind of good enough for what we want to do, it's fine, right? And we can kind of get the benefit of using multiple automated theorem provers. So I'm primarily using Vampire, which is kind of the strongest ATP at the moment. But of course, there might be other automated theorem provers that are like have complementary strengths to Vampire, and if we kind of use all of them in some kind of orchestrated way, we could get even better coverage. Right, so briefly on the kind of semantics of the proof. So I kind of mentioned this already, like if you don't write anything at all, it's left to the ATP. So this is this kind of box step. This happens if you either don't write any proof at all, or you just say, oh, this is trivial or something. This is just left to the ATP in entirety. And there might be something going on where we kind of restrict the global context to something where we kind of prune out things that we might not need. So there's some kind of premise selection going on. Then the next thing is we can kind of manually select premises by saying, well, it follows by ABC, and then only those things are the global premises. So the local things are always included. This is kind of like, if you get to the point where the local premises are too large of a set for the ATP, your proof is probably too long anyways, right? And you should like split it into a separate level or something. So this is kind of the implicit convention here. And then the degenerate case of using specific premises explicitly is by assumption. So let's say we have an assumption A in the theorem statement, and we just showed A implies B in a previous proof step, then we can just say, well, by assumption, the ATP is able to figure this out. And then there's like some special terminals like terminal proof steps, like saying, oh, this just follows immediately from set extensionality. So this is convenient if you're just proving trivial things about sets like the union commutes or something. I don't need to write a long proof. I can just say, well, set extensionality. And I kind of added this because automated theorem proofs are sometimes hesitant to use set extensionality because, well, they could use it on any equality term, right, which might not be desirable. So this is the way of doing it explicitly. And then for the intermediate proof steps, this is very similar to Mizar. So this is Frank will probably have flashbacks to his mathematical vernacular paper. So this is quite similar to that. Maybe to start with this half thing. So this is the kind of the intermediate claims that we saw in the previous proofs that I showed quite often. So we just claim something, and the fact that this actually holds is left to the ATP. And we can kind of do the reverse. So we can reduce something to kind of a simpler statement, and the fact that this reduction is valid is then left to the ATP. So that's kind of the two ways of doing that. But of course, there's also all these other proof steps, so that we can simplify an implication. So if our goal is phi implies psi, then we can assume phi, and we're just left with showing phi. We can do the same thing to show negation, right? If we view the not phi as phi implies bottom. We can do a proof by contradiction, we can do a proof by cases, we can simplify universal goals, and then there's like built-in methods, for example, for epsilon induction in set theory. And so this is like equivalent to, at least in this context, it's equivalent to the axiom of regularity. But this is just a built-in method for induction. And finally, we have this consider step that I already talked about earlier, where we explicitly choose a witness from an existential statement. And again, the fact that this exists is led to the ATP. And for all the steps that have an ATP obligation, we can do the same thing. So these kind of by some explicit things or by assumption, we can do the same thing here by saying, well, we have something by, and then explicit reference. So all these can be kind of refined in the same way as the kind of terminal proof rules. Right, and to maybe give you a brief outlook, so a brief summary. So Naproche-ZF is a continuation of Naproche, but it's a completely new implementation. And of course, Naproche is a continuation of SAT. And the same ideas are kind of carried through, but the main goal is to simply scale the system further. We want to kind of go beyond formalizations that use ad hoc axiomatics to reach a single specific theorem. We want to be able to have like a standard library like you would find in other proof assistants as well. And yeah, it has various new features like structures that I showed to you, but also, for example, inductive definitions, and there's some support for higher logic and things like that. There's some improvements to the controlled language, and the implementation by using this grammar-oriented approach is easier to extend. So if I want to change the language, I can just declaratively add new production rules to this context-free grammar. And then, of course, there's also like slightly easier for the author. So previously, you would have to like explicitly specify the plural form of something, and this is now also done automatically through these paradigms. And yeah, so I think I already mentioned this. Like we kind of get a nice document out of it for free in some sense, right? So ideally, this is still functions as a mathematical text. We have familiar set theoretical foundations, so I'm using basically Tarski-Grothendieck set theory extension of ZF. So if you have an existing kind of very formal textbook that uses set theory, and things are like very easy to translate. And of course, if you're used to, for example, Sledgehammer and Isabel Hall, you know that this is a very convenient way of working, and it's hard to go back if you're used to this style. And then maybe as a slight teaser, I want to show maybe something for 2 weeks, the libraries workshop, working on a translation between controlled language and Mizar. So Mizar is an existing set theoretical proof assistant with a large library, I think over 65,000 theorems across like 3.5 billion lines of harmonization. So this is kind of a teaser. So Mizar uses this quasi-natural language, so not quite controlled language, but like maybe similar in spirit. So above you, for each of these 3 examples, you see the original Mizar, and below you see the kind of controlled language paraphrase. And ideally, we want to be able to go in both directions, so that you can write new Mizar formalizations using controlled language, reusing the existing Mizar library. And we're kind of doing this mapping, so we need like a vocabulary mapping, and there exists kind of so they have a publishing pipeline to output LaTeX. We're kind of reusing the same vocabulary mapping to get something close to this. Right, so this will be maybe a teaser for in 2 weeks or so. And that's it. Thank you.